Okay, now that we're talking about energy, let's do an example and let's see how this is going to work for us. So, in this case, we have a string of length B is attached over this pulley here at point B, this pulley down here, which then has another string attached to it of length C, attached to a mass of M2, so here's M1 and then here's M2. The distance between A and B here, where A is a fixed point, is a distance of 2d, and we're going to define this length of the string here to be x1. Now, in our case, we're going to pretend, or at least take the fact that the strings and the pulleys are both massless, and then use those to perform our calculations. Now, so what we want to determine then is what length x1, we're going to call x0, does this situation then have an equilibrium position? So basically meaning that there's no net force acting onto this system. And we want to know, is this equilibrium a stable or unstable equilibrium? So this is what we want to know. So basically move on, let's define this distance here as x2. And then, of course, when we're talking about here, this is a vertical system, so we have gravitational potential energy. So the only thing we really care about is the potential energy. In this case, where our potential energy we're going to care about is only gravitational potential energy. Now again, since there's ambiguity, we can define our zero wherever it is that we want our zero to be. So in this case, I'm going to go ahead and define this line that connects A and B together as my y is equal to 0 location. Now, what that means is that, since these are all negative distances down then from that y is equal to 0 location, this and this are both going to have negative potential energies. Which means that, according to this is going to have a potential energy then of minus m1g times the distance, x1, minus then m2 times g times x distance, which is going to be x2 plus that distance of c. Now, since this has a finite string length of b, what that means then is that x1 and x2 are not independent from each other. So x2 is actually dependent on what x1 is. So, first of all, we can figure out what x2 is based on the fact that we know that since the total length of the string is b, and this is taking up a distance of x1, that means the remaining amount of distance across here must be equal then to b minus x1. So this total distance that we have through here then must be equal to b minus x1 is equal to the remaining length. We're going to call that simply L. So L is the total length that goes across here. Now, I probably didn't draw this very well, but this section here is supposed to bisect this entire length, which basically means that this section here should be length over 2, this section should also be length over 2. And since this distance from here to here is twice of the distance d, that means this distance across here is simply d. Now, to make this a little bit easier, let's make a simplifying assumption. Let's assume that our pulleys here are basically point sizes, which means that we're going to ignore the radius of those pulleys. So these things are basically just particular points, so that this thing then is going to create simply a triangle. So in this case, we're then going to have across here, this is our distance x2. Here is going to be d. Across here is going to be our L over 2. So in this case, we simply want to find then that distance of x2. So by Pythagorean's theorem, we know that L over 2 squared must then be equal to d squared plus x2 squared, which means x2 then is going to be equal to the square root, and L over 2 quantity squared minus d squared, or if we plug this in, it's going to be the same thing then, b minus x1 over 2 squared minus d squared square rooted is going to be equal to x2. So this allows us then to parameterize x2 in terms of x1, so now my potential only is going to depend on that value of x1, i.e. simply the length in this case, which is in our case, what we want to extremize. So, in this case, this is going to become minus m1g x1 minus m2g times the square root of b minus x1, all divided by 2, quantity squared minus d squared. So this is our potential as a function of what we call x1. So good. So now we want to seek where this thing has some equilibrium, meaning that the system is static. I keep dropping this eraser, which means that we need to find the places where the force is equal to 0. So in this case, we want the force on the system equal to 0, which means that we want to consider the derivative of our potential with respect to x1. So let's do that. So in this case, this term is going to become simply minus m1g. This term is going to become a little more complicated. So let's write it down. So I get a minus m2g times. So first I need to take the derivative of the square root. So it's going to give me a factor of 1/2. The square root then is going to move to the bottom. So it's going to become the square root of b minus x1 all over 2 quantity squared minus d squared. And then I need to take the derivative of the inside portion, which means in this case this is going to give me a 0, this will be non-zero. So here I'm going to get a 2 times b minus x1 all divided by 4. Good. Now it's 4 because, so again I have to square this whole thing out. So this is going to become a 2 squared, which is going to give me the 4. When I take the derivative of this with the x1, this guy comes down. And then I have to take the derivative of the inside of this, which actually gives me a negative sign. Good. So good. So this is going to make this whole thing a 1/2, which with this one is going to make it a 4th. That's going to make it a positive. So I'm going to get a minus m1g plus m2g divided by 4 times then b minus x1 divided by the square root b minus x1 over 2 quantity squared minus d squared. Now, since all this is equal to 0, of course that means that the g's are all going to go away, so I don't have to worry about the g's. And then from here, I just need to determine what x1 is, or that x1 is then we're going to redefine it to be x0, which is the location of the equilibrium. So basically, all we want to do now is take this derivative. Value at x1 is equal to x0, where x0 is going to be our equilibrium. We're going to set this guy equal to 0, and then solve for x1. So I'll save you some algebra steps. I'll let you go through the algebra, but basically what we should find is that x0 then is equal to b minus 4 times m1d divided by the square root of 4m1 squared minus m2 squared. So this is our equilibrium position. So it means to have this thing in equilibrium, some sort of equilibrium, the length of this x1 should be equal to x0, which is equal to this length. Now, we want to know, is this a stable or unstable equilibrium position? So, going back to what we just talked about in the previous video, so to know if this thing is stable or unstable, I need to now look at the second derivative of this with respect to x1, evaluate it then at the equilibrium position, which is x0, and then determine if this thing is positive or negative. Again, if it's positive, that's concave up, that means it's a stable equilibrium. If it's negative, that means concave down, which is going to give me an unstable equilibrium. So, let's do that here. This. So we want to first look at the derivative, or the second derivative with respect to x1, which is equal to the first derivative with respect to x1 of that first derivative. So let's plug that guy into here. So it's going to be minus m1g plus m2g over 4 times b minus x1 all divided by the square root b minus x1 divided by 2 quantity squared minus d squared. Review and get rid of all of this. So now when I take the derivative of this term is simply going to go to 0 since there's no x1 terms on there. This, as far as x1 is concerned, simply a constant. So this term goes to 0. This term is also a constant, so I can pull it outside of the derivative. So it's going to be the same thing then as m2g over 4 times the derivative with respect to x1 of b minus x1 divided by the square root b minus x1 over 2 quantity squared minus d squared. So this is basically a product of two functions. My first function is b minus x1. My second function is b minus x1 over 2, quantity squared minus d squared, all raised to minus a half. It's always a lot easier to do the product rule as opposed to the quotient rule, but let's do it that way. So remember that if I have a product of two functions, take the derivative of those, so that a of x times b of x, that's then equal to the derivative of the first function times the second function plus the first function times the derivative of the second function. So here, my first function, a, is simply equal to what? B minus x1. And again, my second function is equal to b minus x1 divided by 2 quantity squared minus b squared, all raised to the minus half. So when I take the derivative of the first one, again, b is simply equal to a constant. I have an x1, so this becomes simply negative 1. So the first term is going to become into g over 4 times then, so I get a negative 1 times b. So it's going to be simply negative 1 over the square root b minus x1 over 2 quantity squared minus d squared. Plus the second, plus the first, which is then b minus x1, times the derivative of the second. Take the derivative of this, so I get the negative half comes down, so I get minus 1 half. And then I get times the function, so this is going to be a b minus x1 over 2 squared minus d squared, so the minus 3 halves, so that's that one, times the derivative of the inside, so the derivative of the inside again is going to give me a 2 times b minus x1 all over 4. So from here, common denominator between the two of those is 1 over that term to the 3 halves, which means I multiply top and bottom of this by this term, and then simplify. So again, I'll save you some steps. What we should find in this case then is this works out to be square root of 2m2gd squared all over b minus x1 quantity squared minus 4 times d squared all raised to the 3 halves power. Okay. So this is my second derivative. So now, all we need to do is take this second derivative, evaluate this at x1 is equal to x0, and then simplify. So if I do that, so again, I'll save you some algebra steps, but let's take this thing and evaluate it at x1 is equal to x0. This works out being g times 4 times m1 squared minus m2 squared, all divided by 4 times m2 squared times d. So this is my concavity at this particular point. Now, what we can see from here is that what? For this thing to be a stable equilibrium, we have to have that this term then is bigger than this term. So for a stable equilibrium, our condition then is that m1 squared must be greater, or 4m1 squared must be greater than m2 squared. If this is true, this is going to be some sort of stable equilibrium. For unstable equilibrium, in this case, m2 squared must be greater than 4m1 squared. In that case, this thing would be negative, and since it's negative, that would have concavity down, so this would be an unstable equilibrium. So this thing will reach an equilibrium position as long as 4 times m1 squared is greater than m2 squared. If this is true, this will be stable equilibrium. If that is not true, so if m2 squared is greater than 4 times m1 squared, then this will find itself in an unstable equilibrium. So once it establishes equilibrium, if I just look at it wrong, it's going to go shifting and move to some other position. So no longer be in a static situation. Now, typically what's going to happen is anytime I have more than one object, so here I have these two masses, what will typically happen is one of these distances, in this case that's x2, can be parameterized in terms of x1. So in this case, even though this is a two-body problem, at the end of the day, I can always reparameterize one of those variables in terms of the other one, which allows me then to have a function of only one variable. This will pretty much be true for almost any 2 or 3 or 4 body situations. We can always parameterize in terms of one variable, at least in one dimension.